Okay, so some of this might seem familiar from like the first couple of days of this unit where we were talking about energy and thermodynamics and stuff like that. Okay, work energy theorem is probably the most important concept there is in high school physics. Okay, possibly physics, classical physics in general, because it explains how things happen. Right? It explains where the energy comes from to make something move, or how something moving can do work on something else and transfer energy to it. Okay, so it is the classical mechanical explanation for basically all movement. All right, so it's going to be pretty important that we understand how it works. All right, so we need to understand work energy theorem, that work and energy can be equal, but that one cannot exist without the other, and even more importantly, that work is a change in mechanical energy. Could I have picked a worse color for that? Probably. That's worse, isn't it? Which one's harder to see, the blue or the red?
Blue.
The blue? Purple. Purple okay? I don't know. None of them look really good. There's chromostereopsis. It's that thing where opposite ends of the spectrum makes it hard to see. Okay, so work is a change in mechanical energy, okay, and that's going to mean basically that we're going final energy minus initial energy, because that's what we've learned delta always stands for. Delta always means change, which is final minus initial. Okay. We need to understand kinetic and potential energy, so the two types of energy that make up mechanical energy, because mechanical energy is the sum of an object's potential and kinetic energy. Which is, again, something we learned in the first couple of days of this unit. Okay. And the last thing that we're going to go over is the relationship between force and work. So while work is a change in mechanical energy and can be calculated by going final minus initial, it can also be calculated by doing this. Multiplying force by distance. Okay? Now, you're probably looking at that and going, geez, that's all Greek. It's going to seem that way at first. Okay? But think about it this way. If I were to, let's say, take this, we'll use my chair, that's better. Okay, so right now, does my chair have any energy? None. It's on the floor, it can't fall any further, it's not moving, okay? But if I push it, will it move? Okay, so if I give it just like a little push, it moves a little bit. Okay, did I do some work? Yeah. Okay, because I made it move. I exerted a force through a distance. Okay, that force was very small, and so was the distance. I basically just extended my arm, so maybe over 30 centimeters. Okay, was the distance over which I exerted my force. Okay, if I exert a lot more force, will I do more work? Okay, there's the relationship between force and work. More force, more work. Okay, would the same be true for distance? Yeah, it would be. Okay, if we go back to the chair, okay, I only pushed until my arms were extended, right? So that was a short distance. What if I continued to exert that force, but I did it over a greater distance? Do I do more work? I do. Chair went further. Not because I released it further, but because it also went further. Okay, everybody all right with that idea? That's work energy theorem in a nutshell. Okay? Work is dependent on the change in energy, the force exerted, the distance over which the force is exerted. Okay? All right. Okay, here's a pretty classic example of work energy theorem. The mouse. Okay? In this condition does the mousetrap have energy? This is, by the way, the loaded condition. Yeah. Where's that energy stored?
In the spring.
In the spring. Okay. How did the spring get its energy? What do you have to do to load the mousetrap?
You may pull it back and let it click it set.
Right. Okay. So the parts of the mousetrap are the spring, okay, the trigger bar, that's this long thing here, the trigger itself, and, well, this has a very appropriate name, the killing bar.
Oh.
Yeah, because that's what it does. That's the part that snaps the neck of the little mouse that goes in. Okay, so in order to get the killing bar into this position, I grab it and I push back on it, which changes the shape of the spring. It loads the spring. In moving that bar, am I doing work? Yeah, because I'm exerting a force through a distance on it, and then I'm locking it in place with the locking bar or the trigger bar. Okay, and then when something comes and steps on this, the trigger will be released, okay, and the spring will do work on the mouse, changing its shape. Okay. So it's a perfect example of exerting a force through a distance and giving something energy. Okay, once we do that, then the mousetrap has the ability to do work. Okay, because we've done work on it. We've transferred energy from ourselves to the mousetrap. And now the mousetrap has that energy and it can transfer it to some unfortunate thing. Okay, everyone kind of follow the idea there. All right, that's the idea behind work energy theorem. When I do work, I give some of my energy away. I transfer it to something else, or I turn it into something else. Okay? It goes from being, mechanical energy in my hands to elastic potential energy in the spring. Okay? All right. If I held this out here, does it have energy? What kind?
Potential.
Right, gravitational potential, right, because it could fall. Right? Can this ever have elastic potential energy? It's not elastic by nature, right? There's nothing I can do that would result in it having stored elastic potential energy, because if I change its shape, it's not going to want to go back to its original shape. That's kind of how you get elastic potential energy. Something has to be able to have its shape changed and then go back. Look at bow and arrow, for example. Okay, not the arrow, the bow. Okay, when you draw back the string on a bow, you pull the ends together. The bow wants to go back to its original shape, so if you let go of the string, it will. Okay, you're changing its shape. It has elastic potential energy in it. Springs are the same. If you compress them or you stretch them, you're changing their shape and they want to go back. Okay, everybody all right with that? Okay, now a lot of sports, and thus sports equipment, relies on work energy theory. Okay, for example, a tennis serve, which you can see here is done in kind of a stop motion kind of thing here. Okay, why in tennis do they use a racket and not a paddle? And don't say because that would be pickleball. Yes, obviously.
Because of the elasticity of the strings.
Yeah, elasticity of the springs is the work energy theorem part of it. The other part of it is you can swing that way faster. Okay, a racket swings faster because there's no air resistance, right? It goes through the mesh instead of around the paddle. Okay? But the big thing is that because it's got that mesh on it, if I'm looking at it from the side, when the ball hits it, the mesh goes back behind the frame and the ball sits in. It's kind of an exaggeration, but it goes back a ways. Okay? When it's sitting in the mesh, I can exert force on it. Would it stay in that mesh for a greater distance than if it hit the face of a paddle? And that's the advantage of a racket. Okay? In any racket sport, the distance over which you can exert the force, okay, is increased, and thus you can hit the ball faster than you could with a paddle. Okay? There's also going to be some elastic potential energy in the strings of the racket that will also be part of that equation that wouldn't be there on a hard-based paddle. Okay, everyone kind of follow me there? So part of how fast you can serve is your own strength. How much force can you exert? Okay? That's kind of a fixed value based on your strength. Your technique can affect the distance part. Okay? Your equipment and your technique. if you've got good technique and you keep your eye on the ball and you get it right in the middle of the racket, okay, all that kind of stuff, then you're gonna have a great serve because you're gonna maximize the distance, maximize the force, and do lots of work and get lots of kinetic energy out of it. If your technique isn't very good, maybe you hit the edge, right, the frame of the racket instead, maybe shank the serve off to the side, okay, you don't get a lot of speed on it because you're not maximizing all of that stuff, okay? In hockey, same idea, right? Modern composite hockey sticks are vastly different than what I had when I was a kid, okay? When I was a kid, everybody's stick was the same. It was a hunk of tree, okay? They were all wood, right? They were heavy, they were not very flexible, okay? And so there was kind of a maximum speed at which anyone could really, shoot a hockey puck with it. Now with those composite sticks that do explode far more often than wooden sticks do, okay? But they are far better in terms of the distance over which you can exert your force. So if I'm looking at like an old style wooden stick, okay, it's got a bit of flex. It might be able to flex that much, which would mean that arc there would be the distance over which, let's say, a professional hockey player could exert their force. You give that same professional hockey player a composite stick, and you've got almost double the flexible range in that composite stick. Okay? It's why, in the last few weeks here, they're with the Stanley Cup playoffs, they've been showing the speed of their shots. Okay? There are lots of slap shots that are over 90 miles an hour. Okay? You don't generally have too many guys do that with a heavy wooden stick. Okay? But their wrist shots are also way faster than anyone shot it with a wooden stick, okay? Making goaltending a lot more difficult. So they gave goalies more pads, bigger pads. You ever watch back when Gretzky played? Everybody had goalies had pads that were barely wider than their legs. Okay? Very different game, right? But that equipment change is a big deal. Okay? Basically any sport, okay, you look at can have some application of this. Golf would be another one. Okay? Now, you've got flex in the shaft of the club, and you also have that the ball is softer. And when the ball is softer, it meshes, kind of flattens onto the face of the club and stays on the club face for a little bit longer. It gets a little bit of elastic potential energy and then flies off the face of the club versus hitting an old ball, which was like hitting a rock. Okay? So all those little things. Basically, the only sport that has not embraced any of this is baseball. It is still a hunk of horse thrown at a hunk of wood. Okay, so a guy stands and swings a hunk of wood at a hunk of horse, okay, and tries to hit it. Right? Now, baseball has of course embraced other sciences. That kind? Yeah. That's the science they embrace. Can you tell I'm not a big fan of baseball? I don't get it. Maybe it's just two guys playing catch for 3 hours. I like watching the highlights because then I see all the exciting parts in about 30 seconds. Okay, that makes sense? All right, now, what if, because in baseball this also happens, what's the advantage of corking your bat?
It'll go off the bat faster.
Goes off the bat a little bit faster. What else can you do with the bat? Good, no one said hit someone. If it's hollowed out and filled with cork, it's lighter. You can swing it faster. Okay? The danger though is you hit a dinger with it and it'll explode. Okay? It loses a bit of its structural integrity if you don't do it right. That's how they caught what was his name, Bonds. Okay? Because he was corking his bats and then he hit a big home run and the bat exploded and the ump picked it up and found it hollow. He was like, ooh, cheater. Yeah. Okay? All right, but all of that kind of embraces this work energy theorem idea, okay? Basically all sports do that. Some of them use it for their protective equipment, okay? Helmets and pads and all of that. Okay, so work is related to the force acting on an object. The greater the force, the more work you are going to do because of this formula. Work equals force times distance. So the greater the force, the greater the distance. Okay? The more force you can exert, the more work you can do. So the stronger you are, okay, the better. Okay? Mass can also affect the amount of work done because if something has more mass, it can have more energy. Okay, mass is a part of energy, so the more massive something is, generally the more energy it can have. Okay, and then of course the distance. Okay, if we're looking at a bow and arrow, okay, and you drew it back this far versus this far, okay, which one would shoot the arrow further? The second one, yeah, because you're putting more work into the bow stores more energy and transfers that back to the arrow. Okay, we come back to the bow and arrow and slingshot and catapult, all of those, we come back to those all the time with work energy theorem because they're exactly how work energy theorem works. The more force or the more distance, the greater the energy you're going to give the object that you're launching. Okay. All right. So, here's the idea. Okay. This formula here, force is mass times acceleration, is actually Newton's second law. Okay. But if I have a person who, is, let's say, a professional golfer, they line up to swing and hit the golf club, or hit the golf ball, sorry. Okay. Here's the amount of force they can exert if they swing as hard as they can. They're exerting that force on a very small mass, because the golf ball is very small. Okay. So as a result, the golf ball is going to have a very large acceleration. Everybody okay with that? Now, let's say for whatever reason, they decide a golf ball is not a challenge, so they're going to wind up and smoke this truck. Okay? Same amount of force, same golfer. But now he's hitting an incredibly large mass. So he's going to produce a much smaller acceleration. Okay? Now, you're probably always going, yeah, Coderre, if he hits that truck, the truck isn't going to move. The club will explode, and the truck won't move. Well, in the real world, yep, you're right. The truck isn't going to move like roll or slide. Okay? But if it was on completely frictionless ice, would it move then? If I did this in outer space, would it move? Absolutely. Okay? I would produce an acceleration, but that acceleration would be incredibly small. Okay? Now, on Earth, in the real world, he hits this, the truck doesn't move. Does that mean he didn't do any work? He still did work. Will there be a dent in the truck? Okay, the dent counts, that's work. He changed the shape of the truck, okay, that still counts as work. And he actually does get the truck to move. He just doesn't get it to roll. If I'm standing here and I put my hand on the front of the truck, do I know when he hits it? Because, yeah, I can hear him hit it, and I can also feel it. If the vibration travels through the truck, every single particle in that truck moved. Okay? They didn't move all together, okay, and make the truck actually move, but the truck vibrated. Okay? That means that the energy, the work he did was turned into sound, vibration, other things like that, okay, other forms of energy. Still counts as work. Okay, everybody all right with that? John? Yep. All right, now, motion doesn't just mean the movement of an object, like we just said with the truck example. The truck doesn't have to move, okay? Its shape changed, that counts, okay? So an object can be compressed, it can be stretched, as long as the atoms are moved around, okay? We still count that as a work being done or a change in mechanical energy, okay? So if I have a static spring where I'm not compressing or stretching it, it would have no energy. But as soon as I try and stretch it, or as soon as I try and compress it, it's going to want to go back to its original shape. Okay. All right, now, we talked about this also on like the second day of this unit. Okay, work and heat are both transfers of energy. All right. Work deals with mechanical energy, whereas heat deals with what kind of energy? Starts with T. Thermal. Okay, so they work in the same way. They're transfers of energy. It's just what kind of energy they're transferring. Okay, and we need to kind of understand that those two work in the same way with different kinds of energy. Okay, so if I, bring a candle up to something, you can feel the thermal energy coming off of it. It's transferring from the flame to the air, to your hands, okay, or whatever, okay? Versus with mechanical energy, it would be someone comes up and pushes on your hand, okay? That would be a change in mechanical energy. Okay, so potential energy is something you have due to position or condition. Elastic potential energy deals with condition. That would be the desire to go back to a different shape, okay, being stretched or compressed or some other way altered. Whereas gravitational potential energy has to do with position. You have gravitational potential energy as long as you can do what? Fall. Yep. If you can fall, you have gravitational potential energy. Okay. Now, if I put this pen on the desk, you would probably say, well, clearly it can't fall. It's in the middle of the desk. You're right. But if I was to move it over towards the edge, it still has the same amount of potential energy. It's above the ground. Anytime something is above the ground, it can fall. Even if it's on something else, it can still fall. All right. And so it has gravitational potential energy because of that. That's the energy we're going to deal with the most. Okay? Now, gravitational potential energy depends on three things. Okay, that formula is on your formula sheet. It's the formula for gravitational potential energy. It tells us that the three things that affect gravitational potential energy are mass, acceleration due to gravity, g, and height. Okay? So, here's how mass affects gravitational potential energy. The more mass something has, the more energy it has. Okay? Imagine this situation. You're standing under a crane. Okay? The crane has a grand piano hanging from it. Okay? Beside the grand piano, another crane is holding a tennis ball. I think I used this example before. I don't know if you guys remember it. Okay? And both of them are falling. The cranes both fail and both things are falling. Which one would I rather get hit by? The tennis ball. Okay? They're both going to go the same speed by the time they get to the ground. Okay? They're both the same height above the ground. They're both on Earth, so they have the same gravitational acceleration. But the tennis ball has almost no mass. Okay? It is very, very light. If it hits me, it's not going to hurt me too badly. Okay? If I stand underneath that piano, that's going to end badly. All right? It has way more mass, therefore it has more energy, and energy is the ability to do work. That work would be the changing of my shape in an undesirable way. Okay? Now, that's mass. More mass, more energy. I mean, that one's kind of the obvious one. We have this inherited kind of understanding that big things are dangerous. Okay, like, if you got a little bird flying towards you and a bus flying towards you, the bird is less dangerous. We recognize that immediately. It's just instinctual. Okay. Now, acceleration due to gravity.
Oh,
No, okay. Acceleration due to gravity is another one. We have kind of an inherent understanding of this. We know and have this inherent sort of understanding that falling is bad. And if we fall from a significant distance, we'll get hurt because falling means you'll go really fast. Okay? And so that has to do with acceleration due to gravity. On Earth, what's this number? We learned it last week. Right. So that's what you're going to use pretty much every single time. Okay? Unless I specify it's on the moon where gravity is 1.6 meters per second squared, or on Mars where it's 3.27 meters per second squared. It's going to be 9.81 because we're going to deal with stuff on Earth. Okay? And then the last one is height. Okay? We also have kind of a genetic understanding of heights are dangerous. I could fall. And the higher I am, the more dangerous it is. Okay? Most people don't get too afraid if they're standing on the bottom stair of a stairwell. Okay? You're not going to, you could get hurt a little bit, but you're probably not going to die falling from that height. But if you're 3 floors up and looking over the railing, that's a little different. Okay? We understand that height, that means I could build up a lot of speed before I get to the ground. Height is scary. Height height implies a certain amount of energy. Okay, so those are the three things that can affect the energy. And they come in these units. Mass is always going to be in kilograms. Acceleration is always meters per second squared. And height is always in meters. Okay, which means I get these units. Kilogram meters squared per second squared. Does that sound difficult to remember? That's a joule. Okay? A joule is a kilogram meter squared per second squared. So most of the time, you'll just write J for joules. Right. The reason I bring this up is just in case we're manipulating this to find something else. Like if we're manipulating for height, we'd be dividing m times g over. We'd be left with m because these things would come over to the other side. Okay? Everyone kind of follow me there? All right, so that's gravitational potential energy. All right, this diagram here. The two blocks are exactly the same mass, okay? One of them is going to be lifted to the top of the ramp. The other one's going to be pushed along the ramp to the top, and the ramp is frictionless. Who does more work? Okay, one pushing it. That's a trick question. What kind of energy do those blocks have once they're at the top? Right, gravitational potential energy. They will both have gravitational potential energy when they get to the top. Okay, and gravitational potential energy comes from mass, gravity, and height. Will they both be the same height above the ground when they're at the top? And I said previously that they have the same mass. And G obviously has to be the same for both of them. When they get to the top, they both have the same amount of energy. Well, if work is a change in energy, then it's the same amount of work, regardless of how you get it to the top. Okay? So they both do the same amount of work, getting it to the top. Who uses less force? Like, which one would be harder? Lifting that big heavy thing to the top or pushing it up a frictionless ramp to the top? Which would be harder? Lifting it, yeah. Okay, because work is also force times distance. This distance here is shorter than this one. Okay, so this person uses a greater force over a smaller distance. This person uses a smaller force over a greater distance. But in the end, they do the same amount of work because they change the energy of the block by the same amount. That's the whole reason why the inclined plane is one of the simplest machines. It allows us to do work we couldn't do otherwise. Okay? Like, I might not be strong enough to lift that block, directly lift it up over my head and set it on top of it. I might not be strong enough to do that. I can't exert enough force. But I could probably exert this much force. I just have to exert it over a greater distance. Okay? That's how an inclined plane works. Okay? It means that you don't need as much force, but you have to exert that force over a greater distance. It's how the Egyptians built the pyramids. They didn't have help from aliens. Okay? They had lots of sand to build ramps and lots of slaves to move the bricks. I'm not saying that that's a good thing, but that's how they did it. Okay? Really, really long ramps. Like if you ever like look at any of the architectural or sorry, archaeological stuff, they say that basically they just made a ramp that kept going around and around. As the pyramid got taller, they just added to the ramp, okay? And they built it kind of spiraling up, and then they just removed all the sand, all the ramp from there. Okay. Everyone all right with that idea? Okay, so this is kind of some of the simple machine stuff and how it works. Okay, let's say I've got this situation here where I've got the 5 kilogram ball and the 3 kilogram box. Okay, so if I pull the 3 kilogram box back so that this ball can fall, and it's 2 meters above the ground, and I'm just holding on to the ball, does that system have energy? If I let go of the ball, what will happen? It'll fall, and it'll possibly it'll bounce, but if the ball is attached over a pulley to the 3 kilogram mass, if I let go of the ball will fall and the box will? It'll move, yeah, it'll slide. Okay, so in this system then, the energy is basically in the ball to start with, but when the ball starts to fall, it exerts a force on the box. But the system's energy stays the same. The ball will lose some, okay? The box will gain some as it moves, but the whole system's energy won't change. All right. So this is the formula we talked about it just a minute ago. Potential energy is mass times acceleration due to gravity times height, okay? And that height is usually measured from the ground. Okay, so let's do a kind of a simple example here. So I have a 3 kilogram box, and it's lifted by an upward force 1.5 meters above the surface of the earth to the top of a table. What's the potential energy of the box in its new position? So I would want to use m times g times h, because I know I'm lifting it. Okay, I'm giving it potential energy. Take the mass, multiply by g, multiply by height. Okay, and I would get that that box now has 44.1 joules of potential energy. So how much work did I do? If I'm the person who lifted it, how much work did I do? Don't overthink it. 44.1 joules worth of work. Remember this. We said this earlier. Work is a change in energy. The box gained 44.1 joules of energy. Where did it get it from? It got it from me. I lifted it. Okay? So if it gained 44.1 joules of energy, it's because I gave it 44.1 joules of energy by doing work, lifting it up to the top of that table. Okay? Everybody all right with that? All right. Now, if I needed to solve for something other than the potential energy, let's say I was given the potential energy like I am here. Sorry, that's supposed to be 5.40 times 10 to the 3 joules. Now, maybe let's talk quickly here about scientific notation, because I think this was giving people trouble earlier. Okay, if I write this number here, okay, that number is in scientific notation. Proper scientific notation means I have a base number that's between 1 and 9.9. And then I put on it however many powers of 10 I've multiplied it by to get that. Okay, so in this case, this number is not 5.4. It's 5.4 times 10 to the power of 3. What's 10 times 10 times 10? 1,000. So this number is actually 5,400 joules. Okay, this 3 is how many places I move the decimal to find out the real number. Okay? We use scientific notation a lot in physics because we deal with lots of really, really, really big numbers and lots of really, really, really small numbers. Like, you know, the mass of the Earth. Oh, sorry, 5.98 times 10 to the 24 kilograms. It's a lot. Okay? That means it's 5.98 with 22 other numbers behind it before the decimal. Okay? It's big. Okay? Or things that are really, really small. Like the mass of an electron. 9.11 times 10 to the minus 31 kilograms. That means take this decimal and move it 31 places that way. Okay? So it's 0.00030 times 911. Okay? That would be the mass of an electron. Okay? Everyone kind of follow how the scientific notation works? Okay. Now, you can punch that into your calculator the same way we did with Avogadro's number back in the chemistry unit. So in case you've forgotten how that works, okay, we can just put it in our calculator. Eventually. Like so. Brackets 5.4, hit the second function button, hit the comma button, so you get the little e, okay, and 3. Okay. I do that, 1,400. Okay, so in this particular problem, we have 5,400 joules worth of potential energy, and we know the mass of the diver, 55 kilograms. Right? They want us to calculate the height. So if I want to get height by itself, what do I do with m and g? Okay, I want to isolate height. What do I do with m and g to get height by itself? Divide, because I'm multiplying all three things together. Right? So I divide both sides by m times g. Now I'm solving for height. So with the numbers we had in that question, 5,400 joules, okay, divided by 55 kilograms times g, which is 9.81. I should get that that person is standing on top of the 10-meter platform. Everybody all right with that? Is that a pretty easy formula to manipulate? Yeah, whatever you're solving for, divide everything else over because it's all being multiplied. Okay, let me give you guys about a 3-minute break here, and then I got a couple of videos for us to watch. Let me come back. So when we're talking about kinetic energy, it's got to do with 2 things. Okay, whereas potential energy had to do with 3 things: mass, gravity, and height. Kinetic energy only depends on 2 things: mass and speed. Okay, so 1/2 mv squared calculates our kinetic energy. Now, the really important thing to remember here, to understand, is that speed is squared in that formula. Okay, so any increase in speed results in an exponential increase in kinetic energy. Okay, and we'll go over, I'll explain in a little bit more detail tomorrow, but we'll go over like a mathematical example of what that does to your stopping distance in a car. Okay, because what it comes down to, anytime you're trying to stop, you're doing work. Okay, if you're trying to stop, you're trying to change your kinetic energy. And that can only be done by doing work, which is force times distance. Okay, changing your kinetic energy to 0 so that you're stopped. Okay, now your force is basically whatever force is stopping you. So your brakes, okay, is basically your only braking force, right? So you bring that over to this side, okay, and you'd be solving for how far you would travel before you stopped. Okay, that would be dependent on the road conditions, obviously how much friction there would be, whether it's icy or dry, okay, but also on how fast you're going and how big of a vehicle you're driving. Obviously, you can stop a Honda Civic a lot faster than you can stop a semi-trailer. Okay, because it's gonna have way less mass, right? Semi-trucks have really big brakes, way more friction, but there's just more of them to stop, right? So that mass factor comes in there. The more mass, the harder it is to stop because it has more energy. The faster it's going, the harder it is to stop because it has more energy. Okay, is that sort of making sense? Okay, so tomorrow is quiz day. So you will have a quiz on acceleration, 2 questions. I'll post the questions as well as a solution video today. And then we'll go more into kinetic energy tomorrow. And then we're going to be doing a lab. Wednesday, I think, is the day I have the computers booked on work. Okay, it's pretty simple. And then we're going to continue on with work and energy here up until our unit exam, which will be May 31st. Okay, so make sure you've got that date in your phone so you know it's coming.